You see my white screen, yeah? Okay. So what this all about? So I derived some while ago normal forms for three bifurcations which appear in 1D case, which are whatever fold bifurcation, which is also known as tangent bifurcation and also known as saddle node bifurcation. Then it was transcritical bifurcation and pitchfork bifurcation. But as I said, in 2D case, we have one more bifurcation, Hopf bifurcation. It happens like this. So maybe I will show it. I don't know if I've shown this on diagram. So we have this 2D case, x dot equals to of xy, y dot is u of xy, and then when after linearization we get x dot y dot equals to Jacobian of x. It's linear case times xy, yeah. And at equilibrium, we will have linear equation, so it's called linearization. And then at equilibrium, what we, I think, trace was here. Determinant was here. And then what we know, based on our knowledge of trace and determinant, we knew that if trace, so trace and determinant's coordinates of point, if this point is somewhere here, which is, so this is trace and determinant of Jacobian, then here we have stable node. Here we have stable spiral. Here we have unstable spiral. Here we have unstable. Unstable node. And here saddle. Then these three bifurcations which we know, they take place. They take place here. Yeah. So what if determinant is 0 of our Jacobian? So we can put it this way. So for either fold or transcritical or pitchfork bifurcation to take place, determinant should be 0 at equilibrium. So this is it's another way of saying this is hyperbolic equilibrium. Yeah. So because if determinant is 0, determinant of Jacobian 0 means that one of lambdas, let's say lambda 1 is 0. It is easy to check. So one of lambda should be 0. Another is not 0. It's kind of not necessarily 0. And so this, and here we have these three hour bifurcations. I will call it saddle node, transcritical, and pitchfork. And there is one more place where equilibrium, stability of equilibrium changes at this point, this line, when stable spiral transfers to unstable, other way around. So trace of J equals to 0 and determinant of J positive. So here these are conditions for so-called Hopf bifurcation. Okay, but if we consider Hopf bifurcation in, for example, in linear system, we don't see any limit cycles. So for limit cycles to occur, there should be some extra conditions. And I can, so for with these extra conditions, generally some combination of second of and third derivatives of this f and g should not be zero. It's called first Lyapunov exponent. So there are two conditions. One condition, okay, so let's put it like this. I'll okay, I will clean it. Now x dot is f of xy. And now since we talk about bifurcations, should be parameter c. So now we have these cases. Now for Hopf bifurcation, so first of all, after so we should assume at zero, let's say 0. When x equals to 0, y equals to 0, and say c equals to 0, we can always bring, you remember this. So if we have bifurcation somewhere else, or hyperbolic equilibrium somewhere else, we can always bring it to the origin. And so what it should be, so we have Jacobian at 0, 0, let's put it like this. And Jacobian should have lambda 1, 2, alpha. I can put alpha is function of c plus minus I times beta function of c. And okay, b1, 2, I will keep this also, b real. So it is eigenvectors plus minus I, b imaginary. And they also functions of c. Now, one condition, well, I will derive these conditions for Hopf bifurcation, hopefully, if I remember this correctly. And then what we say, okay, if let's consider linear case first, x dot e and y dot equal to a times xy. So I will start on one page. X dot y dot equals to a times xy. And we assume that lambda 1, 2 is alpha plus minus I beta, and b1, 2 is b real plus minus I b imaginary. So this means that we have focus at the origin. Yeah, stable focus. One step. If alpha is 0, it would be a circle. And now we know that if we make transition, let's put it like this, UV, no. So X, Y, I did it at some point, you can check it again. B real, B imaginary, UY. So this is change of variables or substitution. With this change of variables, we will have for U and V following equations. U and V equals to, let's say, alpha minus beta, beta alpha, UV. So this transfers into this. No, this transfers into this. With this kind of substitution. And this matrix is called normal Jordan. Okay, normal Jordan form. matrix A. So if matrix A, any matrix A which has this kind of eigenvalues, alpha plus minus I beta, with the same alphas and betas, many different matrices could have same eigenvalues. They all eventually can be transferred into this form, and therefore this matrix is in Jordan form is common for all of them. Yeah, so this is it's material from linear algebra somehow. Now assume, now we will consider this case. Now we consider u v equals to alpha u. Maybe I will put it like this. U dot equals to alpha u minus beta v, and v dot equals to beta u plus alpha v. So this is what we get in this Jordan form at the end linear system. And now what we will do, so this is also common technique, we introduce variable z. And this variable z is complex variable, and we will put it like this, u plus iv. And then complex conjugate of z will be u minus iv. So this, it's another change of variables. Then from here we can find, let's find from here, if we add them up, then and divide by 2, it will be u. So u will be equal to z plus complex conjugate of z divided by 2. Yeah, we just, if we add these two equalities, we will have z plus complex conjugate of z equals to 2u, or u equals to z plus complex conjugate of z divided by 2. On the other hand, if we subtract from one from another, we will have 2iv. Therefore, v will be equal to z minus z complex conjugate of z divided by 2I. I think it's correct. This is what we get after the substitutions. And now what we can say, okay, now we can put it here back. So u dot is equal to z dot plus complex conjugate of z dot over 2. And this will be equal to alpha times z plus complex conjugate of z divided by 2. It is u minus beta times z minus complex conjugate of z divided by 2i. Is it okay what I'm talking about? I don't know if you say something. If you can stop me if you get confused with any point. Do you understand what I'm doing? Anyone? At least can you follow what I'm doing?
Yes. Yes.
Yeah. Okay. So what it was? We had this. We had, I can tell. So we had this originally. X dot u dot equals to a x u. Then we transferred it into this. We made change of variables and came here. And now I am changing variables to get in terms of z, these equations. So for first equation transfers into this, and second equation will be z minus z complex conjugate of z over 2i dot derivatives will be equal to beta times u z plus complex conjugate of z over 2 plus alpha times z minus complex conjugate of z over 2i. So this is what we got. Now let us multiply. So this guy we should multiply by I times I. we will have z minus complex conjugate of z derivative over 2 will be equal to b times z plus complex conjugate of z over 2 times I. And here will be plus alpha times z minus complex conjugate of z over 2. Yeah, so this is, I just multiplied by I, this equation. So I disappears here, I disappears here, but I appears here. Now what we will do, so we have two equations. First equation is this, and second equation is this. So if we add up these two equations, what we will get? If we add up these two equations, on the left-hand side, we will have z dot, and on the right-hand side, it will be alpha times z plus z dot. So this first term here, this plus this will give us alpha z. On the other hand, this and this, what it will give? Can you see what it will give? So they where to put it? I will try to free space here. So you have it already, and anyway, so it's recorded. So what I want to do, I want to check this. So what we have minus beta times z minus z conjugate over 2I plus beta times z plus z conjugate divided by 2 and times I. So if we multiply by I first equation, so here, what I want to do, I will multiply here by I and here also by I. So I multiply numerator and denominator by I, so nothing will change, yeah? But then if we do this, we get here minus beta over 2I squared. I squared is minus, therefore it will be plus beta times z minus z conjugate times I divided by 2 plus beta times z plus z conjugate over 2 again times I. So that what we see is here minus complex conjugate of z plus complex conjugate of z in these two cases. So this guy and this guy cancel, and we will have beta zi. So I will put it here now. Plus I beta z. So alpha plus I beta is lambda. Yeah, so I will call it lambda times z. So this is what we got at the end. So these two equations, what color to use? Right, okay. These two equations transferred into z dot equals to lambda z. So this was my point, my aim. So I was aiming this. Okay, so this is, it was preliminary story, and now we will talk about how it should go. So we have z dot equals to lambda z. It is for linear case. So in fact, if we had, let's say, x dot is of fxy, y dot is g of xy. So this could be linear path, derivative of f over x times x plus derivative of f over y times y plus, let's say, I will call it f2. So this is a remainder, which is second and higher orders. Here will be a derivative of g over x times x plus derivative of g over y times y plus all as a reminder. So this is linear path. This is linear path, and this is a nonlinear path, second order, third order, and whatever. And then if I will do whatever I did before, eventually here we will have second, third order, so reminder. So I will call it okay, f capital of z. And this f capital of z doesn't have linear path. So f capital of z is this. Generally, it will be like I will put it like this: a times z squared plus, say, b times z conjugate plus c times z conjugate squared. So this is all second order terms, and then there will be a. This will be, I don't know how to call it, d z cube e z squared z complex conjugate f is busy anyway, z conjugate squared and plus g z conjugate cube. Does it make sense? Is it okay? Any question? I don't know how many of you are now. 5 students, yeah, okay. Well, and stop me if you miss any point, because I never delivered this piece, and let's say I am not experienced with this piece of material with delivery and with understanding also, so I can easily get something wrong. Is it okay now? Okay, so what we do now, so assume we ignore now cubic terms, we consider quadratic terms, and even we don't consider all quadratic terms. Assume assume, let's say, E is non-zero and everything else is zero. Everything else is zero. Yeah, therefore z dot will be equal to lambda z plus a z squared. So we consider this. It is not final story, but at least to start with, this is what we will start. Maybe I can even start it in new page. So z dot is lambda z plus a z squared. So it is what we got. Yeah. And now, so our goal is to understand whether we can get rid of this quadratic term. What we can do about this quadratic. Ideally, we find substitution or make for substitution. I'm not finding it. I'm telling you what is it. Make substitution to get rid of 8z squared. So, and this substitution is this: z equals to not omega, it's rather w plus, let's say, a small times w squared. Let's put it like this. Assume we could make this substitution. So if we make this substitution, then we can transfer it. We can inverse this substitution. It will be a w squared plus w minus z equals to 0. And from here we can find that W12 equals to -1 plus minus square root of 1 plus 4az divided by 2a, sorry, yeah, so this is what we got. What of this, so again, so we make quadratic, so this is the problem with this substitution which we use. It is quadratic. It means that if we inverse it, if we look for inverse transformation, that eventually we end up with two possibilities. And from these two possibilities, we should pick one. We're picking the case, when z equal to 0 means w equals to 0. And this would mean that we should have plus. This minus and minus will not make it. Yeah. So this means that w should be equal to -1 plus square root of 1 plus 4az divided by 2a. So, and this is fine. Then this is satisfied. This condition is satisfied if we use this inverse substitution. Okay. So this is next point, and finally we will make so we should work on with this. So we have this, it's very complicated substitution. We should do something with this. I will copy it again. So we still work with this. Now we know that this is backward substitution. W was equal to -1 plus square root of 1 plus 4az divided by 2a. And we want to find quadratic approximation of this second order approximation. We want to find it. So to find second order approximation, we will need to find approximation for this. And you remember this is 1 plus 4az to the power of half. And for our functions, it should be equal to, so I will put here formula 1 plus x. It will be 1 plus x over 2. I think it was minus x squared over 8 plus so on. So this is a formula, Taylor expansion or Maclaurin expansion for this. And if we apply it here, instead of x, we should put 4az. It will be 1 plus 2az minus 4 squared 16. It will be 2a squared z squared. So this is what we will use. And therefore, w will be equal to -1 plus 1 plus 2az minus 2a squared z squared divided by 2a. So this cancels, and we will have z minus 2az squared. So this is quadratic approximation. So this is what we got for w. W equals to z. So in fact, I should say approximately here. Z minus 2az squared, I think. So this is what we got. Now we will work with our formula. So what z was lambda z plus 8z squared. You remember? So we trying to simplify this. In order to simplify this, we now use this substitution. Then w dot will be equal to z dot minus. I'm not sure these two. Did I make a mistake about these two? Because
yes, I think the two should cancel.
yeah, these two should
Yeah.
cancel.
Yeah.
Okay. Because 2 appears here. If we take derivative of this, it's 2/8z times z dot. So now 2 is correct. Before 2 was extra. And now z dot we know. So now we put this z dot here and z dot here. It will be lambda z plus 8z squared minus 2a. I will keep z lambda z plus 8z squared. This equals to so if we open brackets, it will be lambda z plus 8z squared minus 2a small lambda z squared. Yeah, and we can ignore last term because it has z cube, so we ignore cubic terms and so forth. So this is lambda times z plus e minus 2a lambda times z squared. So it is w dot. Now we should remember. Now we can put it back. This z. You remember z was equal to w plus aw squared. So we started with this, as you remember, and this was conclusion of this. But now we need to put. So here we have w dot. So therefore here we should have w, and here we should have w. So w dot will be equal to lambda times w plus aw squared plus a minus 2a lambda times w plus aw squared. So what we want to do, we want just to keep quadratic, linear and quadratic terms. Lambda w plus lambda aw squared, and here plus we ignore this because what we do? I missed something here. This should be squared. This should be squared. I forgot about this squared. And therefore, here we will have w squared only, a minus 2a lambda times w squared. So there will be cubic term and fourth degree term. We ignore all of them. We ignore everything which is more than quadratic. And what we can see here, we have minus 2a lambda. Here we have a lambda. Therefore, it will be lambda w plus a minus a lambda times w squared. This is w dot. And now we can see, so we can get rid of second order term if a equals to a lambda. So or a is taken as a capital divided by lambda. Yeah. So what it means, we made this substitution. And in this substitution, if we take a equal to a capital divided by lambda, then eventually we will have this w dot equals to lambda w, and second order term disappears. So this is a substitution to get rid of this term. So let's summarize it. I hope I will remember this. So we got z dot equals to lambda z plus 8z squared. We made substitution, which was z equals to omega plus w plus AW squared. And after this, what we have proven, we've proven that in terms of W, we will have lambda W. We will have linear plus cubic terms. Yeah, so not this disappears. What is interesting, now I will skip this part. If I would have z dot equals to lambda z plus 8z squared plus bz z conjugate plus c z conjugate squared, and I use still the same, then we get in terms of W, we will have lambda W plus eventually, I didn't prove it, so 8z squared disappears, but this and this will stay plus cubic. So what it means that we can, by using this substitution, we can get rid of all this term. And this is only a small piece of getting to the end. Next part of story would be, what if we have z dot equals to lambda z plus b capital z z complex conjugate. I don't, I found it. So then so it says like this, we can introduce again, introduce variable w, which is connected with our variable z like this, c times w conjugate. And we can find value, we can find c such that w dot will be equal to lambda w. So a plus cubic. So same procedure, long procedure, but it's pretty much the same. So this way it means that if we have this term, we can get rid of this. So this c should be equal to c capital divided by lambda. And same story is, by the way, this third story. So this was second story. Third story, z dot is lambda z plus c z capital squared. So in this case, we again use w cw complex conjugate squared, and we get w dot equals to lambda w if here it was, sorry, just to make it consistent, I will call it b small, and here b small, b capital. If so what it should be here, c should be equal to c capital divided by, it is more complicated, 2 lambda complex conjugate divided by lambda. This is about this guy, and about c I made wrong. I think this formula is wrong. I can't find the correct formula. I don't have it, so you can try to find out what it is. Yeah, no, it's correct. B over B lambda. Maybe I have this formula, you can double check it. And I have this formula, it looks quite different from previous. So I'm not quite sure if this is correct, by the way, but we don't have time to check it. Anyway, so this, what it means? It means that we can get rid of all quadratic terms by using this kind of substitutions. These substitutions are very important. It has kind of name, I don't remember how it's called, this kind of substitution. It has a very special name also. And the next part of story, also very long story, is to get rid of cubic terms. So what we have, z dot equals to lambda z plus what I don't remember what a b c, so it was d times say z cube. So if we have cubic term, then eventually we can also get rid of this. So what we do, it is very long. I will just tell you the story like this. If we make substitution z equals to w plus dw cube and d equals to d capital over 2 lambda, then in terms of w, it will be lambda w also. So this cubic term disappears. And the only difference, what it means, so you can do it with dz cube, also can be done. With, so d, let's say, z times complex conjugate squared, z complex conjugate cube, but can't be done with z squared, z complex conjugate. So this, what it means that if we have cubic terms, then eventually we can get rid of everything except for this term. So this means that z dot equals to, let's say, f of z can be transferred to z dot equals to lambda z plus, let's say, I don't remember what it was, okay, say g times z squared z plus fourth order terms. And this guy can appear at any of change of variables we did before. So so if we have second order terms, we should make 3 times change of variables. And in each of these cases, we can get this kind of term, z squared times complex conjugate of z. Then if we have cubic terms, there are, in addition to this, we have 3 other cubic terms. And for each of them, when we try to get rid of them, so this can, I think we can get this. Maybe not, I don't remember. Anyway, so what it means that there are cases when this term doesn't appear. And these cases are degenerative cases when we don't have limit cycle. But if after all these changes of variables, we get this term, and this term is non-zero, then we have non-degenerative term when we will have limit cycle. It could be either stable limit cycle or unstable limit cycle. So this just a minute. So there is again long story before we will get. I will put it like this. So we have z. So okay, we have this form z dot equals to lambda z plus g z squared times z. Now we can introduce r, which is modulus of z, and go, let's say phi. Phi is argument of z. So then this equation can be written in terms of r and phi, and we will have, sorry, r dot equals to alpha r. So I didn't derive it, I just tell briefly the story, plus something times r cube. I don't know what to put here. Gamma. And phi dot equals to beta. So this is what we will get after transition to these variables. So alpha and beta, it is, so we remember it's lambda, alpha plus I beta, it's fine. So this alpha and beta from there, and this gamma comes from G, so G is replaced. So somehow gamma is derived from G. I don't remember how it's derived. So it could be some real part of G or something like this. Don't remember. And now this guy, in terms of this guy, and this now you can recognize when I was considering my case in case study, I got something like this. I got r dot equals to r times alpha plus, oh, I can put, okay, alpha plus gamma times r squared, sorry. And what is interesting here is you can see in terms of r. Okay, I will go to the next page. Assume, so I skipped lots of, it is long derivation, I skipped many things. R times alpha minus, what it was, gamma r squared. So if you look at this equation as it is, you will find out that we have here alpha minus gamma r squared equals to 0. So r squared is alpha over gamma, and r, let's say r1 is 0 here. If we look for equilibria for this, and r2, 3 plus minus square root of alpha over gamma. So this is, in terms of r, we have pitchfork. But the point here is that r is magnitude of z, and this should be, so it's absolute value, it should be positive. Therefore, this minus case, we don't observe minus case when we consider our two-dimensional system. This is gone. So formally, we have pitchfork bifurcation, but in fact, what happens, this plus, so this would be like this in terms of r. If we have some parameter c, then we have r equal to 0. It's one equilibrium, and assume we have two other equilibriums here. It's pitchfork. So since negative r is well, doesn't make any sense. We remove this. And what we see so R equal to 0, it is our equilibrium. And this equilibrium, this should be, by the way, here it should be, for example, unstable. Now, let's put it so here it is unstable because for pitchfork, and then it gets stable. Yeah, for example, like this. And this is subcritical pitchfork, as you can see, because new equilibria are unstable. And this corresponds to limit cycle because it is cycle of radius r. And this is our equilibrium. So we have equilibrium. At equilibrium radius is 0. And then we have limit cycle. And radius of limit cycle is given by this. And this, so for if we had here subcritical pitchfork, I have plotted here, this cycle will be, this limit cycle will be unstable. On the other hand, we can imagine, so if C R, so it could be like this, stable here, unstable here, and stable here. So this is supercritical. Now we remember that this doesn't make sense. So this is stable limit, stable limit cycle. And this is still our equilibrium. And it's what it says when we change parameter. So our stable equilibrium becomes unstable, and we get stable limit cycle. It is supercritical Hopf bifurcation. And here, unstable equilibrium becomes stable. So this was focus, you remember. Unstable focus becomes stable focus. And it is accompanied by formation of unstable limit cycle. This is subcritical. At least, yes, at least it's to some level I was explaining everything, but it turned to be, even for online session, it turned to be too long. So I skipped quite a few things by then, but at least you have some idea how you can come to what means Hopf bifurcation and how it's related to pitchfork bifurcation. And it's why it has common names like subcritical and supercritical. Okay, so this was, I prepared, well, not prepared, I was thinking about talking about this if you don't have any questions. But now I will stop sharing. And I don't see you. And maybe I will stop recording.